Okay, before giving my talk, I just wanted to make this preliminary announcement. I want to stress the preliminary, but ICERM is a new NSF-funded institute, kind of like MSRI and IPAM, that's going to be based in Providence and associated to Brown. And it will be starting up technically next fall, but there's a lead time while everything gets organized. But tentatively, and this is still tentative, but I wanted to announce it so people could put it on their calendar, and partly for people who might want to come, but even more for people who might be thinking of organizing conferences just to try to avoid conflicts. Tentatively, there's going to be a semester devoted to arithmetic dynamics in Providence in the spring of 2012, which will include, probably 3 week-long workshops and maybe some shorter things. I'm almost tempted to let people figure out what ICERM stands for, because at least Larry actually managed to figure it out with no hints. Larry and Matt figured it out. It stands for Institute for Computational and Experimental Research in Mathematics. So there'll be lots of theoretical math done there, but there'll also be sort of integration of computation, especially large-scale experimentation. Because, as you probably know, an awful lot of mathematics first gets discovered by doing examples, and these days examples often require not only massive amounts of computer time, but actually significant ideas simply to program it so that the computer will finish the problem and get you some examples, or get you enough data, especially when you're studying things that converge very slowly. Okay, so I hope to see everyone in Providence in 2012. Okay, so today's topic is good reduction, and Rob's already mentioned good reduction several times. I'm going to pretty much stick to Q for today. At the end, I'll jump up to number fields. So if you have a rational function, as usual, say f over g, and you write it just as a ratio of polynomials, there are a few things you might want to do to kind of normalize this representation. First, certainly you want to assume that the polynomials f and g have no common roots. And in that case, well, also assuming that one of the polynomials has degree d, so this is a map of degree d. But then I can clear denominators from the a's and the b's, and also I can pull out common factors if the a's and b's have a common factor. So I can normalize. Oh, remember I said I was going to stick to working over Q, so I'm thinking of rational coefficients here. I can normalize it so that the GCD of the coefficients taken as a whole is 1. Okay? And having done that, we say that phi has good reduction at a prime p if, when you reduce the curve mod p, by which I mean just reduce all the coefficients mod p, so this would now be a rational function with coefficients in the finite field fp, if this reduced curve still has degree d. So in other words, you see what can happen when you, even though f and g have no common factors, when you reduce mod p, they might well acquire common factors. Okay? Or another bad thing that could happen is both the a and the b, a sub d and b sub d might be divisible by p, and then the degree would go down. That's in some sense acquiring an extra factor at infinity, if you want to think of it that way. Okay? So this is more or less the same as Rob's definition, except I've kind of done it globally with the a's and b's being integers rather than p-adics. Although much of what I do today, you might just as well be working over the p-adics. Okay? An alternative definition is that phi has good reduction at p if and only if p does not divide the resultant of f and g. Remember, after I've normalized it like this. Because the resultant is a polynomial in the coefficients of the, well, all right. The resultant is a polynomial in the a's and the b's that vanishes if and only if f and g have a common root. So this will measure whether the reduction has a common root, or whether the polynomials have a common root mod p. A common factor, well, common factor mod p. Okay, good. Why bother with good reduction? Well, if you have good reduction, then a lot of things are true that you'd like to be true, but actually are false if you don't have good reduction. So a relatively easy proposition is if phi has good reduction, so assume phi has good reduction at p, then reduction commutes with composition. So if you take the nth iterate and reduce mod p, you get the same thing as if you reduce mod p and take the nth iterate. Second, if you take a point and look at where it's mapped to, reduction commutes with evaluation. So if you look at the point phi of alpha and reduce it mod p, that's the same as applying the reduced map to the reduced point. And from these, it's very easy to show that if alpha is a periodic point, say it's periodic of period n, then the reduced point will be periodic for the reduced map. Actually, that may even be true without the good reduction. But what happens is periodic of period, say, m. Well, it's a bit too much to expect that the periods m and n are exactly the same, but you'll get m divides n. And that simply follows by using a and b. All right? And I'll mention the proofs of a and b are relatively easy, either using properties of resultants or using sort of fancier ways of thinking about it. Maybe I'll just mention another way to think of good reduction, which makes some of these things easier, is, so what is phi? Phi is a map from P1 of Q to P1 of Q, right? It's a nice morphism. P1 of Q is the generic fiber of the projective line over Z. This is proj Z. Okay, so now talking about schemes. In general, oh, okay. Now I want to work mod P. So maybe we'll do it p-adically, okay? The map phi does induce a map on the scheme, but in general, it's just a rational map. Okay. I'll call it phi lift. Okay. And phi has good reduction is equivalent to phi lift actually being a morphism. Okay. So if you know little algebraic geometry and like schemes, then hopefully this is very illuminating. And if you don't either know algebraic geometry or hate schemes, you can ignore that because I'm not going to use it again. Okay. So what's the main thing I want to do? Well, really, I want to make this part C more precise here. Okay? And there are many reasons to do this. Sort of a meta-mathematical principle is when you want to study something over Q, you reduce it mod P for lots of primes and see what happens, and then try to lift it to see what's happening globally. And for example, I mean, sort of the nicest possible thing that would happen maybe would be that if you take a point of period n and reduce it mod P, it still has period n. That would be nice. That would kind of say that points of period n don't coalesce when you reduce mod P, which would tell you something, well, if we weren't working over Q, but over Q bar, it would tell you something about ramification of the fields they generate, for example. All right, so with that as motivation, I want to try to study what happens to the period of a periodic point when we reduce modulo a prime. Okay. Here's a theorem. I need to set a bit of notation. So as usual, phi will be a rational map of degree at least 2. P will be a prime. And let me let alpha be a periodic point for phi, a Q-rational periodic point for phi. And I want to know what happens to the period. So let me set the following notation. Let me let n be the period of alpha. So that's the smallest iterate of phi is phi to the n. The smallest iterate that sends alpha to itself is phi to the n. When I reduce alpha mod P, that'll have a period. Let's call it M. The period of alpha tilde for phi tilde. This is all working mod P. Okay. And let me define a third quantity, which there's no reason in the world to define it at the moment. It's just it comes up in the proof. So it's easier to define it now. What I want to do is I want to let R be the period, the order, I guess is really the word I want. The order of, well, I want to take the multiplier of alpha. Remember, that's a certain derivative. But I don't actually quite want to take that. I want to take the multiplier of the reduced point, alpha tilde, for the reduced map. And this will be a number mod P. Right. So remember the definition of this. Since M is the period of alpha tilde, this would be you take the mth iterate of phi tilde, take its derivative, and evaluate it at alpha tilde. Okay. And with the order of this number mod P, just it's multiplicative order, just an FP star. Okay. So that'll be a number dividing P minus 1 because the group has order P minus 1. If by some chance the multiplier is 0, then we'll say R equals infinity. All right, just to set it equal to something. And then the theorem relates these quantities. It says that either the global period is the same as the reduced period, or the global period is the reduced period multiplied by the order of this multiplier, or n is mr times the power of p. Now, yes, I know the last two are essentially the same if I allowed k to be 0, but I kind of like to separate them out. I'm kind of thinking of k at least 1 here. Okay. And this is what I'm going to prove for you. A more careful analysis yields something a bit stronger. It tells you about k. First, if p is at least 5, then k is 0. In other words, if p is 5 or bigger, this last case doesn't even occur. And if p is 2 or 3, then k is at most 1. Okay. This, if you studied elliptic curves, this should look kind of familiar. If you take a torsion point of order n and reduce it mod p, then the order of the, if you have good reduction, then the order of the point will still be n, as long as n is relatively prime to p. But if n is divisible by p, you can lose some p's. So it's the analog of that. In some sense, what makes analyzing dynamics much harder than the elliptic curve case is this stupid R thing here. It's this second case coming up. It's one of the things that makes it harder. I guess there are a lot of things that make it harder. Okay, so there's the theorem. Oh, yes, thank you. I've been talking about good reduction, but I didn't mention it here. Yes, phi has good reduction at p. Yes, it's very much a theorem about good reduction. And if you trace the way through the proof, in fact, you can replace Q by QP, in fact. The same thing's true. And the theorem is completely false if you have bad reduction over the p-adics, as many of the examples Rob did illustrate. Okay. So here's the proof. It's essentially just a bunch of algebra, but so remember, I'm writing my curve like this. Okay. Yeah. Actually, yeah. Okay. So the curve's going to look like that. What am I going to do? Okay. First, we know from that previous proposition that m divides n, right? The order of the period of the reduced point divides the period of the point. So let me replace phi by phi to the m. Okay. And essentially now we replace n by n over m. So you see what happens now, alpha tilde is fixed. So we've basically reduced the case where m equals 1. So that's easy. If now, after we've made this change, n equals 1, we're done. Because then m equals n. Okay. So let's assume that n is strictly bigger than m. The next step is going to be to try to show, well, n is 1 here, of course. The next step will be to try to show that n, the period of our point, is divisible by this number r, because then we'll be able to divide the r out. Okay, so that's where we're headed. To make the computations easier, not strictly necessary, but I'm going to make a change of variables. In other words, replace phi by f inverse phi f for some automorphism so that alpha is the point 0. Okay. Now that's easy to do with an f that's in PGL2 of Q. But it's a little lemma to check that, in fact, you can do that without messing up the good reduction. Okay? So I will leave you to prove that or look it up. That it's possible to change variables, move alpha to 0, while maintaining the good reduction property. Okay. So now 0 is the point we're interested in. It's not necessarily, well, we're assuming it's not fixed by phi, but its reduction is fixed by phi, right? So we're given that phi tilde of, well, 0 tilde, if you like, is 0 tilde. But phi tilde of 0 tilde is just a over b, well, tilde, right? Remember, a naught and b naught are integers. Well, this shows that, so in particular, p has to divide a naught to get some zeros left in the numerator here. And in fact, p has to divide a naught to a bigger power than it divides b naught for this to happen. But notice that if p divides a naught, that implies p doesn't divide b naught. Because if p divided both a naught and b naught, then when you reduce mod p, the constant terms in both numerator and denominator would go away. And you could cancel a z from the numerator and the denominator, the degree would go down, right? So p does not divide b naught because of good reduction. So in other words, and it's easier really to write things out with the p-adics here. So a naught, which was an integer, so I can think of it as a p-adic integer, is in the maximal ideal. And b naught is actually a unit. Okay. Now I'd really actually like a third element, because I'd like to leave the statement of the theorem up, but maybe I'll put this notation up for a minute and then put the statement of the theorem back. All right. So I have this rational function where a naught is in the maximal ideal, b naught's a unit, and if I just kind of do long division, I see that the phi of z, if I start the Taylor series expansion around 0, another way to say it, I guess. So it looks like mu plus lambda z plus some z squared stuff, okay? And because the b naught is a p-adic unit, I can write that. It'll look like, say, this. With, well, let's see. Mu is going to be in the maximal ideal. Lambda, I don't know. Well, I know lambda doesn't have any p's in the denominator, but it's just an integer. I mean, you can work out what lambda would be in terms of the a's and the b's if you want. And these a and b polynomials have integral coefficients. Right. This really comes about because the b naught's a unit here. That's what's driving all this. So you can assume b naught's 1 just by multiplying top and bottom by b inverse. And then you have 1 plus something z in the denominator, and that's what gives you this form. Okay, is that all okay? Just a little bit of algebra. All right. We're trying to figure out where the point 0 goes, what the orbit of 0 looks like, okay? So 0 goes to, well, you plug in mu, goes to, well, you plug mu in, you get mu plus lambda mu plus this god-awful mess. But I'm just going to do this computation modulo, well, essentially modulo p squared, but really modulo mu squared. So you see there's a mu squared here. So, I mean, one way to write it, it's O of mu squared. If you're like, it's something congruent to 0 mod mu squared. And when I plug that in, I'll get mu plus lambda times this thing, plus lambda mu plus lambda squared mu, plus, well, the squared term will have mu squareds in it, plus something that's 0 mod mu squared. So if you just repeat this, and just think about it a little bit, or if you want to be very formal, do an induction. The ith iterative 0 looks like 1 plus lambda squared up to lambda to the I minus 1 times mu, well, mu times that, modulo mu squared. Well, remember, mu is in the maximal ideal, so this is useful information. All right, I haven't used the assumption that 0 is a periodic point, and its period is n. So in particular, phi to the n of 0, by definition, is 0. And that's congruent to mu times this sum, but now up to n minus 1, mod mu squared. Well, and I've got a mu here, so I'm already divisible by 1 mu. So the other term has to be divisible by mu. So we conclude that 1 plus lambda squared up to lambda to the n minus 1 is congruent to 0 mod mu. And now we have to split into two cases. I mean, what is lambda here? Lambda, I mean, was just phi prime of 0. And remember, we've reduced to the case where m is 1. So lambda tilde phi tilde of alpha tilde, we've made the period to be 1 when you reduce mod p, and we've made alpha to be 0. So this is just lambda tilde. And just setting notation, the multiplicative order of lambda tilde mod p is r. Okay? So we're going to split into two cases. So first, suppose r is greater than or equal to 2. But not, actually, I guess you need to do the r equals, and, well, all right, let's do the first case. If lambda tilde is 0, reducing this equation mod p gives you 1 is congruent to 0 mod p. Okay? So that shows that in that case, you know, we're done because this can't happen. Okay? So that's easy. So I'm going to suppose r is finite, but at least 2. So lambda tilde is 1. If you like lambda tilde to the r is 1, but no lower power is 1. Okay. Well, taking this equation here, I'm going to label star because we're going to use it a couple of times, and multiplying it by 1 minus lambda, as one normally does, see, you'll get 1 is congruent to lambda to the n mod mu, so certainly mod p, because p divides mu. So this says that lambda has, the order of lambda mod p divides n. Right? So lambda to the n is congruent to 1 mod p, but lambda to the r is the smallest power of lambda that's congruent to 1 mod p. Therefore, r divides n. Right? That's kind of what we were looking for, remember? Kind of came out for free. So, what do? We now know that r divides n. So let's replace phi by phi to the r and replace n by n over r. And what that will do is it will replace lambda becomes lambda to the r. Because the multiplier of an iterate is just the power of the multiplier. The multiplier is the linear term, the Taylor expansion. So that's just how that would go. Okay. So what we've now done is we forced our lambda, now that we've replaced lambda by lambda to the r, now our lambda tilde is 1, or equivalent. Lambda is congruent to 1 mod p. Okay. If the n we've gotten is 1, remember we took our original n and we divided it by m, and we've now divided it by r. So if what's left is 1, we're done. We're in this case. N was m times r, and we've divided them out. So let's suppose not. Suppose n is bigger than 1. Well, remember, I'm in the case that lambda is congruent to 1 mod p. So let me go back to this formula, this star formula, which was just a general formula. Oh, by the way, I mean since I replaced phi by phi to the r, I mean, you'll have a different polynomial a and a different polynomial b here. That's all right. So star is true, but lambda is congruent to 1. So when I reduce mod p, all the lambdas become 1. So what do I get? I get 1 plus 1 plus 1 is congruent to 0 mod p. And how many 1s are there? There are n of them. So p divides n. So now you look back at the theorem and say, oh yes, now I've divided a p off from n, in this case. So we can replace phi by phi to the p, and replace n by n over p. If n is 1, you're done. Else, use star again. Well, I moved it again, but that equation will again give you that n divides p. Okay? So just repeating this, you just get p divides n, p squared divides n, and so on. And eventually you have to get down to n equals 1 after you've divided out enough p's. Okay? So that shows that the final possible form for this period n is m times r times the power of p. Any questions about that? Okay? Good. What about this bit? Well, I'm not going to do the, well, I was about to say I'm not going to do the whole proof. I'm really not going to do any of the proof. I'm just going to indicate where you go with it. To do the p greater than or equal to 5 case, remember we expanded phi as a Taylor series. So it was a mu term that was 0 mod p, and then the multiplier, and then the quadratic term. Yeah. What you need to do, in fact, is be a little more careful. And take the quadratic term in the Taylor series expansion. And then try to figure out a formula for the ith iterative 0. I mean, it'll start with mu 1 plus lambda to the I minus 1 as usual. But then there'll be some other stuff, mu squared. And then you want to do the calculation mod mu cubed. Okay? You have to figure out what goes there and look at it. And by doing that, you can get a handle on the power of p. On the power of p that divides n. However, some binomial coefficients come up, okay? And if p is 5 or bigger, then they're not too bad and you can control them. When p equals 2 or 3, it's much more complicated. And actually, I'm not 100% sure you can do the p equals 2 and 3 case with just the z cubed term. You might actually need to use the z to the 4th term. Okay? But the moral is clear. You take a certain part of the Taylor series expansion and then see what the iteration does and keep track of what's happening. Okay? All right. So, any questions about that? That's okay? Good. So here's a really cute corollary. I showed you last time Northcott's proof that there are only finitely many periodic points, rational periodic points. But and I talked about, uniform boundedness for the number of such points. Here's a bound that, and actually a method that usually lets you find all of the rational periodic points without much trouble. It's not completely uniform, but it's still pretty nice. So let's let phi, as usual, be a rational map. Let me let p be any prime of good reduction for phi. And remember, another way, I mean, you can find those primes simply if you write phi as a ratio of polynomials, and where the coefficients are relatively prime, then it just suffices to choose any prime that doesn't divide the resultant of f and g. The resultant is easy enough to compute, well, at least on a computer. It's kind of a messy formula, but a computer will compute it for you if the degree is not too big. And you'll get some integer here. And just, for example, take the smallest prime that doesn't divide that integer. Okay. And suppose that you have a periodic point for phi that has exact period n. Okay. Then n is less than or equal to p cubed minus p. And in fact, if p is 5 or bigger, n is less than or equal to p squared minus 1. So for example, I mean, just take a rational map, compute this resultant, and suppose 5 doesn't divide the resultant. Then it has no points of period bigger than 24. And in principle, it's not that hard to check if there are points of period, from 1 up to 24. So this would actually give you a way of pretty effectively finding all of the periodic points. The proofs of triviality, well, using the theorem, this is a corollary. What's the point? Well, let me use the same notation. So n is the period of alpha, and m is the period of alpha tilde, and r is the order of this number mod p. Okay? Okay. Let me first point out that m is at most p plus 1. Why is that? Well, because you're looking at the period of alpha tilde in projective space over fp. Well, I mean, how big an orbit can a point have in a finite set? The biggest orbit is it hits every point once, right? And P1 of Fp has P plus 1 points. So that's the biggest possible orbit. Well, how big can R be? Well, R is less than or equal to P minus 1. And in fact, you can actually get a more careful estimate. R has to divide P minus 1. Why? Because you're looking at this number in the multiplicative group mod P, and you're just asking for its order, and this group has order P minus 1. So the worst possible case would be if n is m times r times p to the k, but we know the exponent k is never bigger than 1. And actually it's 0 if p is at least 5. So that says that n, which is mr p to the k, we have k is at most 1, m is at most p plus 1, r is at most p minus 1, and then you just multiply them and you get that. Okay. And if you're actually going to do this in practice, the way to do it is not just to use sort of a coarse upper bound like this, but use much more strongly. I mean, you have your alpha. Well, you don't have alpha. What you would do is look at the dynamics of phi tilde on P1 of Fp. So it maps that to itself. And just look at the periods that you can get for this particular example. You just write it down. And whatever periods you get, those are the only possible m's that you can have in this theorem. And similarly, you take the periodic points here and you compute their multipliers and just check the orders of their multipliers, and those are the only possible r's. I mean, by the time you get done with this, if p is like 7 or 11, you'll only have a handful of possibilities for m and r. And then you just check whether those actually occur as Q-rational periodic points. Okay, so this is quite an effective way of actually computing the rational periodic points. Why is this not a proof of uniform boundedness? I mean, it's pretty close. Uniform boundedness would say that the period is bounded by something that's independent of the rational map. It only depends on the degree of the rational map. Here we have an upper bound. Actually, it doesn't depend on the degree of the rational map at all, but it does depend on finding, say, the smallest prime of good reduction. Okay? So to turn it around, the only way you're going to find a counterexample to uniform boundedness is looking at a sequence of rational maps of degree D that have bad reduction at sort of all of the initial primes for more and more of the initial primes. Okay? Because as soon as you get one prime of good reduction, you get this bound for the possible periods. And interestingly, the same thing's true for elliptic curves. And I mean, it's even stronger than this. But that little jump going from an almost uniform bound, one might call this, to actual full uniformity is really hard. Really, really hard. And the methods are entirely different. Okay. Maybe I'll leave this up. Is it out of focus? See? It works. It's magic. All right. I've restricted to Q for the talk simply because I think it's easier in a talk to present something like that. There is a general result. The general result up to this double line I just drew, the proof goes exactly the same. So it fits on one page, essentially. I mean, it took me maybe 3 slides, but it fits on a page or so. So let me state that. And then I will give you the part below the line, which is quite hard. So theorem. I mean, let's do this p-adically, I guess. So take a p-adic, a finite extension of QP, and let E be the ramification index. Okay. And roughly speaking, as E gets bigger, things get much harder. And I want essentially the same setup as over there. So I'm going to take a rational map of degree at least 2. And I'm going to assume I have good reduction at P. Well, I guess I don't really have to say at P here because with p-adic coefficients, there is only one prime. And this is, I mean, you can essentially use the definition I was using or the definition Rob was using. You just want to write the numerator and denominator polynomials. So all the coefficients are p-adic integers, and one of them is a p-adic unit, so you can't factor any more p's out. Okay. And using the same notation as here, so n will be the period of alpha. Oh, I guess I didn't say what alpha was. Alpha is a periodic point of phi that's defined over k. So we let n be the period of alpha. We let m be the period of the reduced point alpha tilde, phi, for phi tilde, which is phi mod p. We'll let r be, as before, the order of the multiplier, which again is just the derivative of the mth iterate evaluated at alpha. So the order of this in the residue field. I'll adopt Rob's notation. Little k is the residue field of capital K. Residue. Multiplicative group. Then either n equals m or n equals mr. Well, that was a bad thing to do, by the way, because I'm also going to use k for the exponent here. mrp to the k. And as I said, the proof of this is exactly the same. It's using the Taylor series expansion up through the linear term modulo the quadratic term. But now the hard part is if you want to try to get some sort of bound on k, you need to take more terms in the Taylor expansion. And of course, you're substituting those Taylor expansions into each other, because you're iterating it. And the number of terms you need to take depends on this ramification index. And also to some extent on how big p is. Okay? And the estimate for k is that it's less than, let me make sure I actually get this correct, 2 times the ramification index over p minus 1. Which, again, if you worked with elliptic curves, this is very similar to what happens with the p-power torsion when you reduce mod p. These are the kinds of bounds ones get. Similar. Actually, in that case, there's no 2. You can strengthen this a little bit. Actually, if p equals 2, in fact, you can remove the 2 from the numerator. Okay? So the first half up to here, actually, I don't even know who this is due to. It follows the lines of classical proofs in complex dynamics. But this bottom half, which is very, very hard, is due to Mike Zeev. And is Mike here? Yes, hiding out. As far as I know, the only place it has appeared is in Michael's thesis, yes? Yeah, okay. The proof, I mean, is this horrendously complicated computation. It's really a tour de force of working with power series and binomial coefficients. Is it available on the web? Is it downloadable on your website? Listed, okay, but the link might not be there. So I think I speak for Michael. I certainly speak for myself. It would be very nice if someone would come up with a more transparent, somewhat shorter proof and then publish it, so it's in the literature. Because it's a very, very useful estimate for many things. Otherwise, it's going to become one of those apocryphal theorems that's true, but there's no published proof. All right. Good. Okay. So I was actually hoping that this material would take like 40 minutes because the stuff for tomorrow, I'm afraid, is going to take 60. So I was going to do the first 10 today. But of course,